This is Coding Math, episode 33, Line Intersections, part 2. In the last episode, we wrote a function that returned the point where two lines intersect. To recap, we looked at different ways that lines could be represented, and derived the intersection using the standard form for a line, ax plus by equals c. Our function takes 4 xy points to describe the lines, so we also looked at how to convert from points to the standard form. At the end of the last episode, I brought up 3 use cases where the function we created will fail. First, of course, is line segments. The formula assumes infinite length lines, so it does not limit the intersection to the area of the line contained in a segment. Second is parallel lines, which will have no point of intersection. And finally, collinear lines, or line segments, will intersect on an infinite number of points. First, let's look at the parallel and collinear cases and see what the function returns in those cases. I'll return to the file we ended off with last time, renamed to parallel.js. Here, I'll change the first line to run between 100-100 and 500-100, and the second line to run parallel and just below that at 100-200 and 500-200. And after we get the intersect point, I'll log the x and y of that point. I'll run that and check the console. And we see that the intersect x and y comes out as minus infinity and not a number. Well, that for sure is not a valid point. So let's dig in and see what's going on. In the line intersect function, let's log the denominator and test that. And we see that the denominator is 0. Well, that would make sense. Dividing by 0 gives you not a number or infinity values in JS. And why is the denominator 0? Well, remember that the a and b values in the standard form basically represent the slope of the line. If the two lines are parallel, then they'll have the same slope. Thus, their a's and b's will be equivalent. To get the denominator, we multiply a1 by b2 and a2 by b1 and subtract. If the slope is the same, those two values will be the same and we'll get 0. So 0 denominator means parallel lines means no intersection. Now the question is, what do you do in the function if you find there's no intersection? Well, there are various possibilities. I'm not going to argue architecture or best practices with you. Do what you think is best. Here I'm just going to check if the denominator equals 0, and if so, return null. In the code that runs this function, I can now throw the result of that function in an if statement and only draw circles if there is a valid intersection. I could run a test of this, but you wouldn't see any difference because as soon as you get anywhere close to parallel, the intersect point is way off the screen anyway. But feel free to put some log statements or breakpoints in there to verify that it's all working correctly. Okay, we've handled parallel lines, now on to collinear. Actually, collinear is a piece of cake. Collinear lines are also parallel. Since they're the same line, they have the same slope. So as it stands, this function will return null. As far as I'm concerned, that works for me. If I'm calling this function, I want a single point of intersection. With collinear lines, I'm not going to get that. So it's fine if null represents collinear or parallel. However, if you did want to return something else to indicate this, you could work out a way to determine this. Since we know the slope is the same, if the y-intercept is the same, then the lines are collinear. If the y-intercept is different, then they are parallel. I'll leave that as an exercise for you to deal with if that's important for you. If so, you might want to arrange some kind of different return types that indicate whether you have a single intersection, parallel lines, or collinear lines. Finally, we need to deal with line segments. Now, there are various ways to do this. I'm not saying the following way is the best, but it should be clear enough and not horribly slow. To demonstrate this, I'm switching over to the interactive version of the program. This will allow us to drag the points around for testing rather than redefining them every time. I've copied over the changes we just made to check for parallel and collinear. Now I'm going to make a whole new function, copying and pasting the line intersection function. Feel free to architect this differently. Maybe you just want to pass in another parameter to indicate that you're dealing with segments, not full lines. I just want to keep them separate for clarity's sake while explaining things. So this function will be called segment intersection. And again, it's a copy and paste of the original. Now let's look at our line intersection. We have line segment P0, P1 going from here to here. Now assume we found an intersection. It's a point somewhere on this overall extended line here. There are three possibilities. It could be up here outside of the segment, somewhere in here within the segment, or down here again outside the segment. We want to know whether or not it's in this middle area defined by the segment. Again, there are lots of ways to do this. The one I came up with is to measure this distance here between the 2 points that define the segment on the x-axis. And then this distance here between this first point and the intersection point, again on the x-axis. And I divide these two. If the resulting number is less than 0, then the intersection point is here, outside the segment. And if it's greater than 1, it's over here, again outside the segment. If it's between 0 and 1 inclusive, then the intersection point is on this line segment. Now where this breaks down is if we have a vertical line. In that case, the x distances will all be 0. So we can follow up with the same check on the y-axis. Of course, that one would fail on a horizontal line, but the segment couldn't be horizontal and vertical at the same time, so one of these will work. Back in the code, I'm going to rearrange this final return statement and use it to make two variables, intersect x and intersect y. Then I'll make a variable rxo, which is the ratio we just talked about on the x-axis. This will be intersect x minus po.x divided by p1.x minus po.x. Then we'll do the same for the y-axis, making ryo intersect y minus poy divided by p1y minus poy. Now we can check if rxo is greater than or equal to 0 and less than or equal to 1. Now again, this might fail for a vertical line, so we'll OR that with a check for ry0 is greater than or equal to 0 and ry0 is less than or equal to 1. If either one of these are true, then the intersection point is within the bounds of that first segment. So we'll return the point made up of intersect x and intersect y. If neither are true, we can just return null. Let's try it. Okay, so initially we have an intersection. If we move P2 up here so the lines don't intersect, the circle goes away. Great. And if I do the opposite, the same thing happens. I can even swap these around and everything works great. However, if I move P2 or P3 like so, then we still get a false positive. So what we need to do is do the same thing for that second line that we just did for the first line. Back in the code, I'll make two more variables, rx1 and ry1, and use P2 and P3 along with the intersection to define them. Then we'll need to AND in another similar clause that compares those ratios to 0 and 1. And that's it. Let's give it the final test. All seems to be working well. Now, my implementation here is a little brute force. I've seen some more elegant solutions using dot or cross products, but they still require a similar amount of code, and to be honest, I'm not sure that they're vastly more efficient. Perhaps when we get around to doing an episode on dot and cross products, I'll use line segment intersections as an example and create a more elegant looking function. In the meantime, this should serve you pretty well as a starter function that you can optimize and tweak, and you can always look for a better one online. At least you'll know what it's doing and how it works. In the next episode, we use this function in some real-world situations.